locality.
Thank you. So we are here at a conference on classical and quantum long-range systems. So far I would say the classical people haven't seen much of what they were hoping to see. And my talk, unfortunately for the classical guys in here, will be on quantum systems. But I will map quantum systems to something that looks like a classical dynamical systems, and I will use methods from classical physics to derive physical properties of the quantum system. So even though the system is quantum mechanical, you may see some classical physics in here, so I'm hoping for the attention of not only the quantum but also the classical people. The topic I'll address is equilibration. So since this is a satellite meeting of the big StatPhys conference, so equilibration is certainly at the heart of statistical physics in some sense. So I hope that this is a topic of general interest that I want to tell you about. The long-range aspect is hidden in the title of my talk in the word locality. So with locality, I'll say a few more words about that later on. A system that is local will be related to something like a short-range interacting system. A system that is non-local, in my language, will have to do at least with long-range interactions in a way that I'll come back to later. So what is the problem I'm addressing? Approach to equilibrium, just consider two systems that are isolated at, say, initially 2 different temperatures, T1, T2. You bring them together, and you expect that the whole system approaches an equilibrium state. This is one of the key assumptions of the foundations of statistical physics or thermodynamics. So this is a topic of interest for the foundations of StatMech, but recently, I will not explain what that plot here is. It's just, many of you might have seen it. There are experiments that, usually in the setting of cold atoms, where the systems are quantistic and very well isolated from their environment, and depending on the details, people sometimes see equilibration as expected, and sometimes they don't see it. Obviously, there's limited timescales available and so on, but there's lots of interest on the experimental side on the question of equilibration as well. What I want to this is switching off and on again. My motivation will be mostly on the question whether for the foundations of statistical physics we can expect to see equilibration happen. And the idea will be ideally I would like to derive thermodynamic behavior from standard quantum mechanics without additional assumption. Obviously that is a big problem to deal with. People have tried for a very long time, and it's a hard problem, but at least on certain aspects I believe we can make progress, and this is what I want to tell you. The setting I'll be considering is isolated quantum systems. So I'm not sure what I can do this work better, but I'll just keep on talking. Sorry, I'll have to ignore this now. I'll consider an isolated quantum system described by some Hamiltonian, and I've written it in a very general form here. This is just a sum over states in the system. These are essentially projectors onto the energy eigenstates. These are energy eigenvalues, and for the notation, for simplicity, I assume that there are no degeneracies, but this is not relevant for the results that I'm going to present. And I'll use the language of a finite dimensional Hilbert space of the total system, which you can think of as a many-body system, and I assume that there's a discrete spectrum, but this is still a very, very class of systems I want to discuss, and the idea would be to derive results not for a specific type of systems, but that are valid in some sense for a large class of systems. So if the dynamics is unitary, and this is what we assume for an isolated system, then there will be no equilibration in the sense of some density operator rho in time approaching some equilibrium state. This is like rigorously true. This cannot happen, and it can be understood fairly simply when if you write down, for example, the expectation value of some observable O in time, and you do this in the energy eigenbasis, then you have the initial state and the matrix elements with respect to the energy eigenstates, the same for the observable, and then you have here an exponential, or like these are essentially oscillations with frequencies given by the differences between energy eigenvalues this time, and the whole thing will be a quasi-periodic function, so it just keeps on oscillating with many different frequencies, and what you get will be a quasi-periodic motion, and you can think of it like this: the expectation value in time will, maybe you start far from equilibrium is down here, it will relax initially and then start having tiny fluctuations around the equilibrium value, but because of the quasi-periodicity, at some very late times you may have rare large fluctuations away from equilibrium. So this is the situation one has to deal with. One could say, well, this is not equilibration because I don't go to equilibrium in the long time limit, but for a physicist this is equilibration, because if these are really rare, these large fluctuations, whenever you measure with some, you'll find equilibrium value within your experimental resolution. So I want to describe this notion of equilibration in some definition, and this is going to be my next slide. Definition 1 is the one I certainly don't want to use. This you find a lot in old literature on, for example, with the ergodic theorem, that people were looking at equilibration in the sense of the long time average of some expectation value. There's two things I don't like about this. The first thing is, according to this definition, a sine function equilibrates, which I find not very convincing. And the second is that the long time average for a physics experiment is not what we are looking at anyway. You may say a real experiment has some time interval over which a measurement is done, but this will be usually not very long compared to the physical timescales of the system, and so I don't find this very convincing. What one can do instead is to define a probabilistic equilibration with respect to the expectation value. So looking at some observable, I say, think of the sketch I've shown you on the previous slide, that I will find it's close to the equilibrium value for most times, and the closeness is here expressed in these wiggle lines, and one can make this notion here precise, what for almost all t means and what these wiggly lines mean. So you can say whenever I'm for most times close to that desired value, I call it equilibrated. And this is, in my opinion, a good definition for some cases. For a macroscopic system, I'm still not happy with it. The reason is that if you have a system that, for example, think of a magnet that can have a plus and minus magnetization, then if you measure sometimes plus 1 and sometimes minus 1, but the expectation value is 0, you would still say, well, this is like, it is equilibrated, even though you never measure that 0 expectation value. So for a macroscopic system, usually you expect even more. You expect that every single measurement that you do will give the expectation value at least to some good accuracy. And this is captured in a slightly more technical definition down here, which I call probabilistic subspace equilibration, and that is the one that I want to use in this talk, because I want to deal with macroscopic systems where I can study equilibration. And what I do here, in the Hilbert space, I look at the eigenvectors of the observable that I choose to monitor, and I take all those vectors from Hilbert space whose eigenvalue does not deviate too much from the equilibrium value, not more than this delta O. And I say these eigenvectors of Hilbert space, they span the equilibrium space, and the others span the non-equilibrium space. I have these two spaces, and I call a state in equilibrium if it's mostly in the equilibrium subspace, and this mostly I express by saying that if that state projected onto the equilibrium space and the trace of it is close to 1, then I would say I'm in equilibrium. And the closeness I can choose essentially by this parameter epsilon. So here I will demand that that the states I'm populating are mostly eigenstate or are superpositions of eigenstates with eigenvalues close to the equilibrium value of that operator. Okay, and before I move to what is known about equilibration, there's one disclaimer. So I'm talking about equilibration, which is a more general notion than thermalization. Thermalization requires you to equilibrate, but that you do so to thermal Gibbs state. And this I'm not talking about. So I only ask whether I'll have equilibration to some state, but I don't discuss the question which state this is. All right, so what is known about equilibration? There has been a lot of progress in the past 15 years or so, having statements about equilibration for broad classes of systems. It's a bit of technical business to tell you how the classes are exactly defined. It's not needed here for us. I'll just give you an idea what people have dealt with and how these results look like. And there's various complementary settings. One is that of macroscopic observables. Again, already this definition is rather technical and goes back to an old paper from Neumann. And this approach has been revived by what I call the Rutgers gang here, with people around Goldstein and Leibowitz. There are other settings. Instead of macroscopic observables, you look at small subsystems of larger systems, or something that I have contributed a little to, global equilibration for physically realistic observables. I don't want to tell you how these are defined here, only to tell you there are a couple of settings for which that you can define clearly and then derive results that essentially tell you on a mathematically rigorous basis that the system will equilibrate in a suitably defined sense. How does such a result look like? Just to give you a flavor of such a result, one can the ratio of times where for some given observable, you find a deviation that is larger than some interval delta O from the equilibrium value. And you calculate the ratio of the times when these rare fluctuations happen. You calculate the ratio with respect to the overall time over which you're conducting the experiment, and you can prove a rigorous upper bound with some expression that is ridiculously small. And by that I mean that for a macroscopic system, it's typically of the order 10 to the minus the number of degrees of freedom. So think of 10 to the minus 10 to the 23 for a macroscopic system. This is so absurdly small that it will not be observed under any circumstances. The shortcoming of these results, in some sense, I think these are very nice results, but there's some shortcoming. The statement is for sufficiently large times t. So it tells you that it will equilibrate after some time in the sense given here, but it doesn't give you the time. If now this sufficiently large time is larger than the age of the universe, you unfortunately have not given good reasons why equilibration is observed in the real world, why it's so ubiquitous in nature. So, and because of this, it's a topic of very much interest at the moment in the field to try to argue or to find bounds on the time at which this happens. And this is what I'm going to deal with. What are meaningful general questions for large classes of systems on equilibration times? Well, when you want something general, of course, there will not be the result, but you can do, I think, two things essentially. Either upper or lower bounds on this equilibration time, or you can ask for the typical time in the sense of random systems chosen according to some measure, harm measure, and some unitaries that create your system, something like this. So either bounds or typical times. And there have been a couple of results in this direction, and there's some I don't mention here at all. There's some from Goldstein, Hara, and Tazaki, which I find very interesting. These are proper theorems, and on the slide I have only given like very sloppy versions of these theorems that are the authors of the paper will never get to see. And in words, I will tell you an even sloppier version of the whole thing. The gist of the first one is that, remember this equilibrium subspace I told you about. So this consists of the eigenstates of the observable that give you expectation values that are close to the equilibrium one. For a fixed Hamiltonian, you can always choose such a subspace such that the corresponding equilibration time for any non-equilibrium state is like ridiculously large, like larger than the age of the universe. So it tells you, this essentially tells you an upper bound, finding a useful upper bound will not work. Same for the bound in the other direction. You can do a different construction, finding that you can always construct such a equilibrium subspace that the corresponding equilibrium time will be ridiculously short, and there's precise phrasings of that, but I will not tell you about. And the last one, so now we have the upper and lower bounds. It wasn't very encouraging, and unfortunately the same is true for the typical equilibration times. For a Haar randomly chosen equilibrium subspace, the typical equilibration time will be of the order of the Boltzmann time, which is this quantity, and this usually will give you something for, say, a physically kind of realistic system in the range of femtoseconds or quite a bit larger. That is not what we observe in nature for most of the macroscopic systems we are familiar with. So unfortunately, these results, nice and rigorous as they are, it didn't give us the answer that we were hoping for, which is a physically realistic equilibration time. And now the authors of the same paper here, Goldstein, Haratazaki, they came up with why this essentially went wrong. And the answer is on the next slide. Well, the conjecture is on the next slide. So locality is what they conjecture is what is missing. So physics is not about typical systems like drawn randomly and or the same is true for observables and states. So locality of the Hamiltonian and the observable should be a crucial ingredient. And I will avoid telling you which definition exactly of locality I'm using. It's a bit of technical business as well, but I just want to tell you, whenever I say it's a local system, the short-range interacting systems that you would think of are included in that class. And if I say it's a non-local system, it includes at least some of the usual long-range systems that you would think about. But the rest is a bit more technical, and we would need to sit down and write these definitions down. The question here is now, what is special about the Hamiltonian and the observable being local? And this is one way you can say what is special. There exists a basis in which both are simultaneously sparse matrices. So if you say if you use the side basis, then this will usually be, both will be a sparse matrix. And this tells you that the matrix elements are not uncorrelated, like in some other random matrix settings, but that they are strongly correlated because of locality. And deriving results restricted to local Hamiltonians and observables is somehow technically harder. There have been a few attempts, not for the equilibration problem, but for other fields, to come up with general tools to deal with local systems, but it's a very recent and not always easy business. So now I want to tell you about my take of how to address this problem. We still haven't seen anything classical yet, so now we're getting to the point. What we chose to, so I just told you that the locality tells you that the matrix representations of the observable and Hamiltonian are not unrelated. So this is why it might be a good idea to use the eigenbasis of, say, the observable and express everything in that eigenbasis, and in that eigenbasis the Hamiltonian is expected to have some special form and properties. And this is what we're doing here. This is, now we write everything, meaning the Schrödinger equation, in the eigenbasis of the observable, which are these OKs. And so this is the wave function as a function of time written in the observable eigenbasis, and this I will call x. This you will see quite a bit on the rest of the slide. And the same I do for the Hamiltonian, and these are the matrix elements of the Hamiltonian with respect to the j and k eigenvector of the observable. Then I can write the Schrödinger equation in this way, and I can integrate it up to give you these equations of motion. We don't gain much by integrating them up, but maybe I think it's useful to see what is happening here. So what we have now, if we think of these xj now as our classical variables, then we have a set of coupled oscillators, and these are the variables, the xj's, and the coupling strength between, so these are other oscillators, xk. The coupling strength is given by the matrix elements jk, by the off-diagonal matrix elements, and the intrinsic frequencies of the oscillators are given by the diagonal elements of the Hamiltonian written in the observable eigenbases. So now we have a coupled set of oscillators, but it's a large set. So if our system had n degrees of freedom, then it's usually then exponentially large in n, because we need one for every state in Hilbert space. So the problem is larger, but it's classical now. This is not new at all. People have done this before, but the question is, of course, what you can do with it. And now, thinking of the sparseness of matrices that I was telling you about before, we'll have a sparse, you can think of this as a sparse network of classical oscillators in Hilbert space. Sparseness because we had local interactions and observables. Now, this is my sketch now. So every point here is supposed to correspond to one of the xj's. I have many of those. I couldn't draw that many. And I've ordered that them in some way according roughly to their observable eigenvalue, like to this, essentially to the value OK that corresponds to an index K. And this is like 0 are those that correspond to equilibrium. And here these are at least not so close to, or still kind of close to equilibrium. These are less close, and this guy here is far from equilibrium. What I've illustrated here as well is what you find is that equilibrium are the majority of the states, and the far from equilibrium are rare states. Now, and I've drawn some lines just between some of those states, and I've drawn not too many because it's supposed to be sparse, and one can work out that there will not be direct connections from equilibrium to furthest non-equilibrium, but we essentially have to go through stages. So this will now tell us something about the problem we have to address. Equilibration as propagation through a sparse network. So to get from far from equilibrium to equilibrium, we have to find a way through this network using the connections that there are, and there will be no direct connections usually. In a system with no locality at all, you will expect to find direct connections from non-equilibrium to equilibrium, and the intuition is that this can happen faster, and that in a local system with a sparse network, it will in general take you longer to equilibrate. And well, so right, so this is the picture of a classical network describing quantum dynamics. And now I skip all the derivations, and I will show you a result that we have derived for this classical network dynamics. The methods we used are related to the Lieb-Robinson bounds that Tommaso talked about this morning, but we use a classical analog of these Lieb-Robinson bounds. So in the quantum version, you had a commutator of a time-evolved observable and a time-constant observable, and you look at the operator norm of it. A naive classical version of that is a Poisson bracket and the absolute value of it. And if you do that and you work, you can write this in a form that looks like this argument here of the logarithm, so this partial derivative. So this is a partial derivative of you asking the question, if you do a slight variation at lattice, or like lattice side k, lattice is that network in Hilbert space, at time 0, how large is the effect on oscillator j at a later time t? This, if you're a classical physicist, must remind you of a Lyapunov exponent, only that they're at different sites, and there is something like co-moving Lyapunov exponents that have been studied in the literature. And it's essentially, it's an object that tells you something like, doing a perturbation here, how long does it take you to feel it on at some other site, and that's very much in the same spirit as the quantum Lieb-Robinson bound. Okay, we couldn't use the existing bounds really for some reasons I'll not tell you about, but we get a result that at least has some similarity to what people find for Lieb-Robinson bounds. And I'll tell you the ingredients that we have. So this is the Hamiltonian. K is a parameter that quantifies the locality of the system in some way. If this parameter, it will be small when the system is very local, and it will be large when the system is non-local. This will be our distance. Distance will be our distance from the equilibrium state, and this is this OK minus OJ. Yeah, and these are essentially the ingredients. If I plot that whole thing, it looks like, oh, I was one click too much. It looks like this. So the shape is, it also has this light cone structure that we've seen before, but it's a cone here, and it's a bit curved further away from the cone. But anyway, it will tell us something about a relevant time scale that we need if we are far from equilibrium to have a chance of seeing equilibrium occur. This is, I tell you now, I'll say a few more sentences, I think, about this. I won't talk about the proof. Yeah, so the interpretation, I think I said this, is an upper bound on how strongly the population at some early time can influence the population at a later time. And now if you think of the point 0 here as you choose it as the equilibrium state, and then if you start out here that's furthest from equilibrium, then it will tell you that you need at least the time on this plot here, 0.6 in whatever units are used to for the oscillation having a chance to travel from non-equilibrium to equilibrium. And this is the earliest time you have a chance of seeing the system equilibrate, and this is written in this equation here. The time at which this happens for some state j and k is given by, or is a lower bound on the equilibration time. The real equilibration time can be a lot longer. And obviously it has to be like this because it's a bound for a broad class of systems. You cannot expect this general bound to give you the right result. You have also included systems where for some reason equilibration takes like forever, but there is at least, according to the bound, for the faster systems, the time should be given by this number here, written down here. When can we expect it to be fast? Well, I would say for a system that corresponds to something chaotic and for a homogeneous initial state. Why homogeneous? Well, if you have a system where you need macroscopic currents of energy or whatever to flow from one part of a macroscopic system to another, this will take a longer time, and this will must scale with the system size in some way. But if you're initially homogeneous, you can still be far from equilibrium, but equilibration can happen locally, and then you might have a chance of seeing the fastest possible equilibration as given by this time here. So where's locality? I told you locality is in the parameter k. Sorry, let me go back. It's in the parameter k up here. What's the effect of locality on the bound? Well, to get a first idea, we can look at the extreme cases of the most local system we can think of, which is one with nearest neighbor interactions, and one can work out that the corresponding equilibration time coming from the bound that we derived scales with the logarithm of the system size. And if we think of the most non-local Hamiltonian, like just random matrix, then we will, according to our bound, we'll find a constant equilibration time. So first thing that we were already quite happy with is that changing the locality character of Hamiltonian observable, we find a significant effect in the equilibration time. And if I may remind you, this is what we set out with according to the conjecture of Goldstein and co-authors, that including locality in deriving results on equilibration times, we would like to see a significant effect. It's not all fine, not all great, it's not always the right type of dependence we want to see, but we have a method where we can include locality in a general result and we can see the effect of locality. We were lucky that I don't want to tell you in detail. If you look at a model with the usual long-range type of interactions, depending like on something like 1 over distance to the power of alpha, this is like some, sure one of the exponents here is wrong. We find agreement of our bound with numerical data, at least qualitatively. So one is off by a factor of roughly 8 or so, but we find the same functional dependence on the long-range parameter alpha. So which tells us our bound is not always great, but it encodes the right functional dependence on the locality, on the long-rangeness of the system. Right, I think that is what I wanted to tell you. A short summary or take-home message is the physics message I want to give you is equilibration time depends on the locality of the Hamiltonian observable, and we can include this in a calculation. In terms of concepts, I very much like this idea of encoding the locality into a sparse network in Hilbert space, and I would believe and hope that there's other things that classical picture of this network. And in terms of methods, if you hadn't seen something like this before, there is Lieb-Robinson bounds. There is a classical version that can be used for quantifying how fast stuff travels through some classical coupled systems. And physics is not typical, I think, is a good message of the whole talk. There is open questions, which mostly tell you we can still do better, and we hope to do better in the future. And with this, I would like to end by saying that Daniel Nicholson is the postdoc who drove much of this project, and most of the credits must go to him. Thank you very much.
Questions? So just bouncing off your remark of other things that could be figured out with this network.